Hi friends, if you place an object like this pencil in front of a convex lens, do you know where the image will be formed? What will be the properties of the image? Or if we replace it with a concave lens, now what is the image going to look like? Actually, I don't need this pencil because in this video, I'm going to be the object and I'm going to go and stand in front of the convex and concave lens. And let's see where my image is formed. I'm going to make the topic of image formation for spherical lenses really easy for you. And as usual, we'll finish off this video with our top 3 questions on this topic. Remember, we have light ray rules for spherical mirrors, and we use these rules to draw a ray diagram and obtain the image. If you haven't watched my video on spherical mirrors, do check it out. Similarly, we have light ray rules for spherical lenses. In this video, we'll be looking at these rules and how to apply them for our ray diagrams. Let's start with the convex lens. The convex lens is a converging lens. For image formation, we need to draw the lens accurately. Let me show you a simple trick for that. Draw a line representing the principal axis. Mark the optical center O roughly in the center of the line. Using a ruler, mark 2 points to the right of O. F2 is, let's say, at 2 centimeters from O, and 2F2 is double the distance. It's at 4 centimeters from O. Similarly, on the left side, mark F1 and 2F1 using the same distance. O is the optical center of the lens, and F1 and F2 are the 2 principal foci of the lens. Now draw the convex lens. You can roughly sketch the lens or use a compass to draw the 2 arcs of the convex lens. Make sure that the lens is thin. Don't draw a thick lens. Now let's take a look at the rules for image formation of a convex lens. Light is a very visual topic, so I would suggest you to keep pausing the video and draw the ray diagrams in your notebook. Then you'll get a much better feel of what is going on. There are 3 rules for the convex lens. Rule 1. A ray of light which is parallel to the principal axis, after refraction, passes through the focus on the other side of the lens. Rule 2. A ray of light passing through the optical center of the lens goes straight. It emerges without any deviation. Rule 3. A ray of light passing through the focus after refraction becomes parallel to the principal axis. Let's place the 3 rules that we have learnt for convex lens on our concept board. Can you see that rule 3 is exactly the opposite of rule 1? It's due to reversibility of light. Remember, when drawing a ray diagram, you need to draw 2 rays from a point on the object. So you need to choose 2 out of the 3 rules. You can choose any 2 rules that are convenient for your diagram. And as I promised, I'm going to be the object and I'll go and stand in front of the convex lens. And you need to apply these rules and find my image. So let's go ahead and try it out. Here I am on the principal axis. I'm far away from the convex lens. I'm going to walk and stand on different places on the principal axis. And as you'll see, my image will change based on my position. So let's start with case 1. I'm standing beyond 2F1. You need to consider the rays from the top of the object. So from my head, remember, we need to select 2 out of the 3 rules. Let's use rule 1. The ray which is parallel to the principal axis after refraction by the lens passes through the focus. So this is our first ray here. For the second ray, let's use rule 2. The ray which passes through the optical center goes straight through, undeviated. So what does the intersection of these two light rays represent? That's right, the image. It's the image of my head, the top of the object, because we considered the light rays from the top of the object. So where is the feet of my image? It's on the principal axis. So you don't need to draw the light rays for the bottom of the image. Simply extend the top of the image to the principal axis and we get the bottom of the image. So as you can see, we found the position of my image here. What are the properties of an image? There are 3 points to consider here. First, is the image real and inverted, or is it virtual and upright? Second, is the image magnified, diminished, or is it the same size as the object? And third, what is the position of the image? So what are the properties of the image here for case 1? That's right, the image is real and inverted. It's diminished. And as you can see, the image is formed between f2 and 2f2. You'll find similar diagrams in your textbook. Of course, I won't be the object there. The object is usually shown with an up arrow, since the object is upright and marked as AB. The image is also shown with an arrow and it's represented as A', B'. As you can see, the arrow is inverted here because the image is an inverted image. Now let me walk closer to the lens. I'm going to stand at 2f1 for our case 2. Once again, we need to use 2 out of the 3 rules. For the first ray, let's use rule 1. The ray of light parallel to the principal axis after refraction passes through the focus of the lens. For the second ray, we can use rule 2. The ray passing through the optical center of the lens goes straight through, undeviated. What are the properties of the image here? Can you see the symmetric nature of the diagram? I'm standing at 2f1 and my image is formed at 2f2. The image height is the same as the object height. That's my height. And can you see that the image is real and inverted? It's a real image because it's formed by the intersection of the rays. If you try drawing the diagram for this case, you might find that the image is not exactly at 2f2. Now this can happen if your foci f1 and f2 and the points 2f1 and 2f2 are not exactly equidistant from each other, or the rays are not accurately drawn. So to avoid such errors, an important exam tip for this case 2 is to use the cheating trick, which is first draw the image and then you draw the rays. Since we know all the properties of the image, we can easily draw it here. It's a real and inverted image, and this image is going to be exactly at 2f2, and the image height is exactly equal to the object height. So once you've drawn the image, you can go ahead and draw the rays. Now I'm going to move closer to the lens. So we have our case 3 here, where the object is between f1 and 2f1. I would suggest you to pause the video here, draw the ray diagram and try to find the image yourself. Also write down the properties of the image formed. So what's the nature of the image you got? That's right. The correct answer is it's a real and inverted image that's magnified. Here's the ray diagram, and as you can see, the position of the image is beyond 2f2. Next, I'll move ahead and stand at the focus of the convex lens. Again, we need to apply 2 out of the 3 rules. This is an interesting case because, as you can see, the refracted rays are parallel. The refracted rays never meet. So where is our image formed? The image is far away, formed at infinity. The image is real and inverted, and it's highly magnified. Now let's look at the final case where I move really close to the lens. The object, that is me, is between the optical center and the focus of the lens. Let's use rule 1 and rule 2 to draw the light rays from the top of the object. As you can see, the refracted rays here are divergent. So we need to produce them backwards to obtain our image. Wow! Can you see? The image is magnified here. So what are the properties of the image? The image is virtual and erect, it's magnified, and it's formed behind the object. Do you know a use of convex lens for this case? That's right, it's used as a magnifying glass, like the one used by Detective Sherlock Holmes. Now that we are done with the convex lens, let's go ahead and take a look at the other type of spherical lens, concave lens. The concave lens is a diverging lens. For image formation, we need to draw the concave lens accurately. Similar to the convex lens, draw a line representing the principal axis. Again, we need to mark the points optical center O and F1, 2F1 and F2 and 2F2. All these points are at the same distance from each other. In this diagram, the distance is 2 centimeters. Note that in a concave lens, usually the F1 and F2 are on the opposite side compared to a convex lens. So F1 and 2F1 are on the right side and F2 and 2F2 are on the left side. You might find different conventions in different textbooks. Now let's draw the concave lens. You can roughly sketch the lens or use a compass to draw the 2 arcs of the concave lens. Make sure the lens is thin. Don't draw a thick lens. Now let's take a look at the rules for image formation of a concave lens. Similar to the convex lens, there are 3 rules for a concave lens. Rule 1. A ray of light which is parallel to the principal axis after refraction appears to be coming from the focus. Rule 2. A ray of light going through the optical center of a concave lens goes straight through without being deviated. Rule 3. A ray of light going towards the focus after refraction becomes parallel to the principal axis. Let's place the 3 rules that we have learnt for concave lens on our concept board. Similar to the convex lens, can you see that rule 3 is exactly the opposite of rule 1? It's due to reversibility of light. To draw the ray diagram, you need to select 2 out of the 3 rules. Once again, I'm going to be the object, and this time I'll stand in front of the concave lens. And you need to apply these rules and find my image. So are you ready? Let's go ahead and try it out. Here I am on the principal axis at a certain distance from the concave lens. Again, we need to take the light rays from the top of the object. So from my head. Remember, we need to use 2 out of the 3 rules. For the first ray, let's use rule 1. The ray that is parallel to the principal axis, after refraction, if we extend the refracted ray backwards, it appears to come from the focus. For the second ray, Let's use rule 2. The ray going towards the optical center goes straight through without being deviated. Now, where do these two refracted rays meet? Since they are divergent rays, we need to produce them backwards. And the point where they meet is the image of my head, because we took the rays from the top of the object. So where are the feet of my image? We don't need to draw rays for that. You simply extend the image, that is the top of the image, to the principal axis and you get the bottom of the image. So as you can see, the image is formed between me, the object, and the concave lens. What are the properties of the image here? That's right, the image is virtual and it's upright. The image is diminished and it's formed between the object and the lens. Now let me walk closer to the lens. If we draw the ray diagram, can you see that we get the image having the similar properties? The image is virtual and upright. The image is diminished and it's formed between the object and the lens. In fact, the concave lens is the easy one in the syllabus because no matter where the object is placed, the image properties will always be the same. But remember, the convex lens had many different cases based on the location of the object. Now that we are done with the topic of image formation for spherical lenses, are you ready for the top 3 questions on this topic coming up for you right now? Friends, practice makes you perfect. So try solving these questions and do let me know your answers and doubts by putting it in the comments below. I promise to reply to all your comments as soon as possible. So I'm going to disappear and you pause the video here and give these questions a shot. And to watch more science and maths videos like these, do check out my website, manochaacademy.com. And if you haven't subscribed to my YouTube channel already, go hit the subscribe button right now. And remember to like and follow my Facebook page. Thanks for watching.